Yes, Faraz. Can you tell me that now?
Ma'am, the folder is not opening. Can you just give me a
Yeah, okay, sure. Sure, take it. Fine. I'm waiting.
Yeah, ma'am. Atoms and molecules 3.1 and 3.2. Ma'am, you're on mute.
Sorry. Yeah. So what I was saying is that in this chapter, we'll be dealing with first point, the historical developments, okay? The historical arguments which regarding the atoms and the molecules. Second, we'll be discussing two very important laws of chemical combination, okay? And third, then we'll be discussing exactly the important, very important, the Dalton's atomic theory. And after Dalton's atomic theory, we'll be discussing somewhat about an atom and then very specifically atomic mass. Okay. So these are some of the topics that we need to learn. Okay. That we need to understand for your syllabus specifically. Okay. Then obviously we have some other parts of the chapter as well. So very quickly starting with the historical developments. Okay. The historical perspectives here. So see, atoms and molecules, there were two philosophies that were going side by side. Okay. One was the Indian philosophy and second was the Greek philosophy. These are the two philosophies which have been mentioned a lot. Okay. Now, see, both of them said the same point. Both of them said the same point. I'll quickly discuss the Indian philosophy first. Okay, but okay. So there was a person called by the name of Maharishi Kannad. Okay, Maharishi Kannad. Okay, he said that everything around us, basically which we have studied in the first chapter as matter, he called that as Padarth. He called that as Padarth. Okay, he said that everything around us is Padarth, and this was in around 500 BC. Okay. And he said that when we keep on dividing Padarth, we can keep on getting smaller and smaller particles, okay, until we reach a point, after which we cannot further divide it, okay, until we reach a point after which it cannot be further divided, okay, and that point after which further division cannot take place, okay, in simple words, that would be the smallest part there, okay, he called that as Parmanu. He called that as Parmanu, okay, simple. Now, there was another other scientist, okay. There was other scientist by the name of Pakuda Katayama, by the name of Pakuda Katayama, okay. He basically gave his ideas on the same philosophy that was given by Maharishi Kannad, okay. He further opinionated, he further expanded the same philosophy, he further expanded the same ideas, and he said that whatever we see around us, around ourselves, that is matter, okay. So it is Parmanu which cannot exist alone, it exists in some combinations, okay. He said that the Parmanu exists in some combined form, okay, in some combined form, and it is through these combined form that we get different forms of matter. According to him, that was Padarth. Okay. So basically, now according to the first chapter, what we have learned in the first and the second chapter, this is all that we have learned in the first and the second chapter. He said that Maharishi Kanyat said that it is the atom or the Parmanu which further could not be divided. And the next opinion or the next idea to the same philosophy was that the atoms would combine or the Parmanu would combine in some combinations to give us matter, right? That we see around ourselves. And this is exactly what we have studied in the first unit. Now, see, there was simultaneously there was this Greek philosophy going on. Okay, the Greek philosophy, and what did the Greek philosopher said that he said that it was Democritus or Leucippus. Okay, they also said the same thing, that when we keep on dividing matter, see the same thing as was said by Maharishi Kanyat, just the terms used are different. He said that everything around us is matter, and if we keep on dividing matter, we will keep on getting smaller stages, but there will come a stage which further could not be divided. And he called that as atom. He called that as atom. Basically, according to him, atom is the last stage after which division cannot take place. So, in simple terms, according to him, atom was the smallest particle there, right? Which was combining together to form matter. Are you getting it? Yes. So, quickly, let's have the NCERT here. Indian philosopher, Indian philosopher Maharishi Kanyat postulated that if we go on dividing matter padarth, okay, we shall get smaller and smaller particles. A stage will come after which the division is not possible. After which the division is not possible, and he named that as Parmanu. Yes, same thing that we have learned right now. Now, what happened? In the same era, ancient Greek philosophers Democritus and Leucippus suggested that if we keep on dividing matter, a stage will come which further after which cannot be divided. And that was called as atom. That was called as. So therefore, Parmanu and atom basically are the same things, right? I got your
Yes.
answer. You said that. Yes, I got you. Fine. So they were the same things, right? Atom and Parmanu were the same. So these were just a philosophy. What is a philosophy? A philosophy is an idea without any concrete proof, without any valid proof as such. Okay, just an idea, just a suggestion. Okay, you getting it? That is what is philosophy. Now the problem was that there was no experimental work to prove all of this. There was no experimental work to prove all of this. It was in the 18th century that the scientists started working on it and to know the difference between all of that. Okay, you know the difference between different forms of the chemicals, elements, compounds, molecules, all of that. Yes, and see, we get the different laws of chemical combination. Now, what are the different laws of chemical combination? See, what did Pakuda Katayama said that the Parmanu was existing in some combination to give us the normal different forms of matter. Therefore, there would be some law, there would be some manner in which the particles would be combining together, right? There would be any fixed pattern if we study that, okay, through which the particles of the Parmanu would be combining together to get us the different forms of matter. And to actually, give reason to all of those ideas, two laws were suggested. One is the law of conservation of mass. First law, bache, is the conservation of mass. First law is the conservation of mass. Now, simply by the name itself, it was given by Lavoisier, Antoine and Lavoisier, in 1774. It was given by Antoine and Lavoisier in 1744. For us, any problem till here? Can you just show me the thumbs up if that's okay? Going fine? Fine. So it was given. Now, what does the law state? See, if you just know by the name, conservation means protection, right? Conservation means protection. So basically, the mass was conserved. Now, the law is based on the fact that mass can neither be created nor destroyed. Mass can neither be created nor destroyed, right?
Yes, ma'am.
Now, if mass would not be created, nor could it be destroyed, then that means if I'm taking some amount of mass, the total mass, okay, for a reaction, if I write the reaction as this, let's say three parmanus are combining together. The total mass of these three parmanus should be the total mass of this padar that I'm getting here. The total mass of all the three atoms should be equal to the total matter that I'm getting here, right? The mass of the total mass of the matter here. Yes, that is how the mass would be conserved. That is how the mass would be conserved, right? So the fact is that the mass, the total mass of the reactant, the total mass of the reactants has to be equal to the total mass of the products, right? Are you getting it? This law was
Yes,
based on this idea.
yes, ma'am.
Okay. And an example, the first question in NCRT within the textbook, okay, within the chapter, the first question is based on this law that certain amount of different reactants are taken and certain amount of products, I mean, certain mass of the products are obtained. Does the law of conservation of mass is followed there? You will have to calculate the total mass of the reactants. You will have to calculate the total mass of the product. If you get the mass as equal, therefore the law is followed there. Yes, the law is valid there. Clear? Now coming on to the second law. This is very important because second law is the law of constant proportion or definite proportions. Okay, fine. Now this was given in 1799. Okay. Now what happened? See, if this is a molecule of water, would you agree with this? If I say that this is a molecule of water, yes. Now in this molecule of water, you have seen in the just a second. So
Yes, ma'am.
yes, sorry for the disturbance for us. Yes. So H2O
Yes,
is a molecule. Okay, H2O is a molecule. We know that from the second chapter we were studying that H2O is a molecule, right? If I take one particle, that is one molecule here, yes, of water, one molecule of water, yes. How many different elements are combining together to form this molecule of water? To form this one molecule of water. How many elements are combining together?
three,
Two, right?
two, yes, two,
Two
ma'am, two.
elements. One is hydrogen element
And
and the
other
other
one is
is
oxygen.
oxygen. Now see, the point here is that when we get the compound or a molecule, you must have studied this in the second chapter, that the properties of the elements are completely different. And when they combine together to give you the molecule or the compound, the properties of the molecule are completely different, right? So therefore, it becomes a completely different particle. It becomes a completely different particle, right? So here, what is the point here? How is hydrogen and oxygen combining together? In what manner, in what ratio, in what proportion to give you water? If I take two molecules of water, H2O, and if I take another molecule of water, H2O, do both of them have the same proportion? I mean, do both of them have the same composition? Absolutely same composition? Yes. Yes. If I take two
Yes,
different molecules of water, will both of them have the same composition? Yes, both of them will have the same composition. Okay. Why? Saying that in each and every molecule of water, whether it is from your part, okay, whether it is from my place, okay, each and every molecule of water will have two elements and these two elements will be combining in a fixed ratio. And what is that ratio? The two atoms of hydrogen and one atom of oxygen to give you this one molecule of water, right? That is what we mean by the fixed proportion. That is what we mean by the fixed proportion. And if we calculate the ratio of the elements by mass, okay, what do we get? For hydrogen to oxygen, it is 1:8, right? Ratio by mass. It is 1:8. You know how do we get this as 1:8? See, I don't know. I'm not able to understand what you are saying, so I'll quickly discuss this here. One molecule of water is this, right? The composition is this H2O. The mass of one hydrogen atom is 1. Therefore, since there are two hydrogen atoms, the mass of hydrogen will be 2. The mass of one oxygen atom is 16. So if I calculate the ratio, I will get 1:8, right? The simplest ratio that we will get for the ratio of elements by mass in the molecule of water is 1:8. Is 1:8. Is it clear to you, beta? Right. Now, what did the law
Yes,
say?
ma'am.
This was about the Pareto law. Now, the law said that the law says that we are not concerned with whatever the source of water is. If I take it from the sea and if I take it from the tap water, in both the cases, water will have, each and every molecule of water will have the same composition, will have a constant, a definite, a fixed proportion, right? Are you getting it? And that is what the law says. Therefore, the law says that the composition of the molecules of the compounds is fixed, has a constant proportion. Clear?
Yes, ma'am.
Example, example, take different molecule, let's say NH3. This is ammonia, right? Wherever you can take ammonia from, we will get each and every molecule of ammonia with the same composition, that one atom of nitrogen and three atoms of hydrogen. Always. Each and every molecule of ammonia will have the same composition. I'm not concerned what is the source of nitrogen, what is the source of hydrogen. No, that is not my concern. I'm saying whenever they are combining together to give you ammonia, this is the proportion. And that's a fixed, a definite proportion, a constant proportion. Clear? Example, let's take carbon
What is
dioxide.
the
What is the
atomic mass of nitrogen?
mass of atomic nitrogen atom is 14. Okay. So the ratio would be what?
Okay,
14
ma'am.
is to 3. The ratio is 14 is to 3, right?
Yes, ma'am.
3 hydrogen atoms, wonderful. Now quickly let's take the example of carbon dioxide. Each and every molecule of carbon dioxide will always have this same proportion. Will always have this constant fixed definite proportion. That is one carbon atom joined with two oxygen atoms, always. Whatever the source of carbon is, whatever the source of oxygen is. But when they are combining together to give you carbon dioxide, it is this proportion that they are combining it. Yes. And if I want to get the ratio by mass, can you tell me the ratio by mass, bacha? See, mass of one carbon atom is 12. And how many oxygen atoms? 2.
16. Sorry, 32.
Right. So can I get the simplest as 3 squared, bacha?
Yes, ma'am.
Right? Excellent. So the point is, if I'm talking about water, whatever whatever water I take, whatever the source of water is, whatever the source of its constituting elements is, I will get the water as H2O. And for each molecule of water, for each 9 grams of water, for each 9 grams of water, I will have one part as of hydrogen and the rest of the 8 parts as of oxygen. Yes. Why? Because I have the ratio as 1:8. Yes, I have the
Yes,
ratio as 1:8. So for every 9 grams of water, 1 gram is hydrogen, the rest 8 grams is oxygen. Yes. So let's quickly take the example. Can you tell me for each 17 grams of ammonia, for each 17 grams of ammonia, what will be the proportion of nitrogen and hydrogen? For each 17 grams of ammonia, what will be the mass of nitrogen and hydrogen in that?
14 parts would go to nitrogen and 3 will be from
For hydrogen.
hydrogen.
Excellent. Okay. So let's quickly take this example. Okay. Let's say I have 4 grams of hydrogen. Okay. I have 4 grams of hydrogen. Okay. With how much grams of oxygen will it combine? With how much grams of oxygen will it combine to give me water? To give me some amount of water.
16 gram.
16. And why 16 grams? See,
Because the ratio of hydrogen and oxygen is 1:8.
yes. So if it is 1:8, Bache, that's right. You are right. You are approaching the question in the right manner. That's fine. But Bache, how do I get that 16 from that ratio?
Um,
If I write the ratio as this, that's absolutely right. Okay. From this ratio, how do I get the mass of oxygen as 16, Bache? Hmm? Any idea? No worries. You can share the ideas. We'll learn it. No worries.
no, ma'am. Actually, I'm unaware of those masses, so that's why
No
I
worries.
have.
No worries. No worries. It's fine. No worries. See, here it's not about the mass. Here it's the proportion. Proportion you should know. Mass we are going to discuss in the later half. Okay. It's the more important part here is of the proportion. Okay. Once you have understood the proportion, I've already told you the proportion for some of the most commonly asked examples. Okay. And it is that proportion that you will have to apply. Example, we know that for every 1 gram of hydrogen, when we are specifically talking about water, that is H2O, right? And the question is also talking about water. So what is the proportion telling to us? The proportion is saying that for every 1 gram of hydrogen, for every, sorry, for every 1 gram of hydrogen, we need 8 grams of oxygen. Yes, just tell me this. For every 1 gram of hydrogen, do I need 8 grams of oxygen? Yes,
Yes, ma'am.
right? If the question is saying 4 grams of hydrogen, how much of oxygen will I need? 8 times of this. Right? This 8 grams is 8 times this, right? So now I will have to need oxygen, which is 8 times of this, right? Are you getting this?
Yes, ma'am.
So how much oxygen
30.
will I need here? X6, 32. Yes, 32 grams. Now if I ask you the total mass of the water molecule, what will that be? 4 grams plus 36 grams. Yeah, I mean, sorry, 32 grams, right? 4 grams plus 32 grams of oxygen. Therefore, the total mass of the water will be
36 grams.
36. And just a very small detail here. If you are able to recall, I just now told you, whenever we have 9 grams of water, whenever we have 9 grams of water, in this 9 grams of water, hydrogen is 1 gram, and oxygen is 8 grams, right? That is why we get 9 grams of water. Now the
Yes.
oxygen and hydrogen here are 4 times of those. See, hydrogen is 4 times, that is again 4 grams. Oxygen is also 4 times, that is 32 grams, right? Then the mass of the water that I'm getting should also be the 4 times. So don't you think 36 grams is actually 4 times the 9 grams? Are you
Yes,
getting
ma'am.
the ratio? Is it
Yes.
understood? Fine.
Yes, ma'am.
Excellent. So coming on to our next example, very similar to this. Okay, very similar to this. If I say, okay, uh, if I say carbon has been taken 12 grams, okay, 12 grams of carbon is there. How much oxygen do I need? How much oxygen do I need to get carbon dioxide? If there is 12 grams of carbon, how much time, oxygen, mass of oxygen will I require here to get the molecule of carbon dioxide? We will just go by the proportion. What is the proportion? 3:8, right? 3:8. So for
Okay,
every
ma'am.
one, yes,
96 grams.
96 grams. How do you do that?
Abhi, eight. It's 8 times of. Um, Sorry.
Is it 8 times of that? I take an easy example first. See, let's say I'm talking about ammonia. Okay, let's say I'm talking about ammonia. Okay, what is the ratio there? 14 is to 3, right? The ratio is 14 is to 3. Fine.
Yes.
Now, if I say I'm having 34 grams of ammonia, 34 grams of ammonia, right? I'm having 34 grams of ammonia and I'm having 28 grams of nitrogen. How much grams of hydrogen do I need here? How much this amount of hydrogen do I need here? But just don't worry. 14 grams of nitrogen combines with 3 grams of hydrogen, right? 14 grams of nitrogen combines with 3 grams of hydrogen.
Yes.
And when this is the ratio, bacha, I get 17 grams of ammonia, right? I get 17 grams of ammonia. How much ammonia do I have right now? Just the double of this, 34 grams, right? 34 grams. How
Yes,
much
ma'am.
nitrogen do I have? Just the double of this, right? How
8
much
grams.
hydrogen can I have? Just the double of this, right? And if I add this, 28 plus 6 grams, what do I get? 34 grams, right? And this is the mass of the product that I have. Are you getting it?
Yes, ma'am. I'm getting it.
Understood? Is it understood?
Yes.
Fine. So in the similar manner, if you approach a question for carbon dioxide, I say there's 3 grams of carbon. I say there's 3 grams of carbon. How much grams of oxygen will I need to get carbon dioxide? Hmm.
Yes, ma'am. Wait a minute.
Yeah, okay, sure. I think there's some network issues, so I'm not able to really get to know your response. No. 'Just go by the
Ma'am,
simple ratio. Yes,
so oxygen is 3 is to 6 or 4 is
but
to
you see,
6?
for carbon dioxide, but it is 3 is to 8. The ratio is 3 is to 8. Okay.
Okay, ma'am. 32 grams
Okay. Let's see. Let's see. Why do you think it is 32 grams?
because here carbon is decreased to 4 times, right?
Okay. See, but I will just tell you one thing. Focus on that. Okay. Whenever we are asked with any question like this, okay, just go by the proportion for that molecule. And here we know that the proportion of two different elements is 3 to 8, right? That is, for every 3 grams of carbon, 8 grams of oxygen will combine. And if this combines, we will get 11 grams of carbon dioxide. Yes, bache? For each 3 grams of carbon, 8 grams of oxygen is combining to that 3 grams of carbon. And therefore, I will get 11 grams this CO2, right? Yes or no?
Yes, ma'am.
Fine. So if I have 3 grams of carbon here, first of all, this was the very easiest part here. I will have 8 grams of oxygen. Yes. Therefore, I will get 11 grams of carbon dioxide. Simple. Is it
Okay,
clear?
ma'am.
Is it clear? Don't go too much into this. This was just for the explanatory part. The point is 2 points there in whatever we have discussed today. So first is that the law of conservation of mass. So for the law of conservation of mass, just add the mass of all the reactants, and that should be equal to the mass of all the products. Okay, mass of reactants, total mass of the reactants should be equal to the total mass of the products. First point. Okay. First point that we've learned today. Second point that we've learned today is that the constant proportion is there. That is, whatever the source of the elements, whatever the source of the molecule is, that we will always have a constant proportion, right? We will always have the constant proportion. And that constant proportion is fixed. Example, for water, what is the constant proportion by mass? That is 1:8, right? For carbon dioxide, that is 3:8. For
Yes.
ammonia, that is 14:3, right? Simple. Clear? So those are the two important points that has been learned in today's class. Inshallah, in the next class, we'll continue from here. We'll continue basically from the Dalton's atomic theory. Okay.
Okay, ma'am. Thanks.
So I would advise you to please go through just this small part of NCRT, so that inshallah in the next class these concepts are clear. Okay.
Okay, ma'am.
And only till 3.2 is your syllabus, right? So inshallah we'll be able to finish it properly. Okay. So just revise.
Okay, ma'am.
Okay. Thank you. Thank you, Bachcha.
Thank
You
you,
may leave.
ma'am. Bye.